Today we're going to talk about section 12.6. So we're going to talk about linear correlation regression. Normally if we were to do this section in class, we would be going much more into detail in the section, talk about some different things that we're just going to kind of skip over in order to save some time at the very end of the semester. So in this section, we're going to learn how to determine whether there is a relationship between two quantities, and if so, how strong that relationship is. Alright, so to start with, some vocab. So the first word that we're going to look at is correlation. Correlation is used to determine whether there is a relationship between two different quantities, and if so, how strong the relationship. We're not going to talk a lot about the strength of our relationship, but we are going to talk a little bit about the whether or not there is a relationship in this section. Again, the strength we would talk about in a normal classroom setting if we were meeting face-to-face, but we're going to kind of shorten some things and leave some parts out. Regression is used to determine the equation that relates two quantities. Before we investigate these, we must discuss some basic concepts. So we're going to talk about a particular type of regression that is going to give us a way to relate two different quantities as we are looking at them. Before we get started off with all of that, we're going to talk a little bit about our scatter diagrams. So our scatter diagram is a graph that shows the relationship between two numerical variables. Data that involve two variables is called bivariate data. The prefix bi meaning two, so we're comparing two different variables together. The x-coordinate we're going to refer to as our independent variable, and our y-coordinate is going to be our dependent variable. Right? Our independent variable can also be called our explanatory or predictor variable. Our dependent variable can also be called a response or a predicted variable. When we're studying scatter plots, we're going to look for three different things. We are going to look at trend, which is kind of like our center for our histograms. Right? We are going to look at strength, which is related to our spread for histograms. And we're also going to look at our shape, which is like our shape for histograms that we saw in the last section where we talked about some different shapes for histograms. Okay. Alright, so let's start with trend. Alright, so let's see if we can fit this all in here. Alright, so the trend of an association is a general tendency of the scatter plot as you scan from left to right. Two variables are positively associated or have positive trends if whenever one variable increases, the value of the other increases. Two variables are negatively associated or have negative trends if whenever the value of one variable increases, that's a tongue twister, the value of the other decreases. So looking at these two different kind of examples here. Here we see an example of positive trend. Right, as x increases, so does y. And here we see an example of negative trend. Right, as x increases, then y decreases. Right, so positive, we're going up. Negative, we are going down. Right, the next thing we're going to look at is we're going to look at strength. Alright, so the strength of an association deals with the amount of vertical variation. Scatter plots with a small amount of scatter or very little variation indicate a strong association. Ones with more scatter indicate a weak association. Right. The stronger the association, the better the explanatory variable x will be at predicting the response variable y. We do have numerical ways to quantify our strength. Again, because we're skipping a little bit in this last section, we're not going to talk too much about those ways to actually quantify or give numbers to how strong something is. But if we compare these two graphs, this one is definitely more spread out, this one is less spread out. So this would be an example of a weaker association. This would be an example of a stronger association. So the last thing to talk about is shape. So the shape of a distribution can be linear or nonlinear. Scatter plots that cluster around a line model a linear trend. And the word linear meaning line, if we look at the first four letters. Scatter plots that are better modeled by a curve, right, we refer to as nonlinear. Right? They are not a straight line. If we look at these next two examples, this first one is a nice straight line, so that would be an example of a linear graph. This one is more of a curved shape, so the curved shape is a nonlinear shape. So as we're just thinking about scatter plots in general, we want to think about these three different things. We want to think about trend, we want to think about strength, we want to think about shape. All right, so in this first example, we're just going to create a scatter plot or scatter diagram. Egan Electric's provided the following daily records about the number of assembly line workers absent and the number of defective parts produced for 6 days. Right, sketch a scatter diagram and discuss the trend. Okay, so looking at this, the way this table is set up, we are going to assume that our X value is the number of workers absent. Right, and then our Y is going to be the number of defective parts. Right, then what we're going to do is we're going to use what we know about our basic algebra skills, and we're going to plot these points. So 3 workers absent means 15 defective parts. So we're going to plot 3, 15. Our next point is 5, 22. So 5 approximate about where 22 would be. Right, 0, 7 it would be right about there. 1, 12 would be right around there. 2, 20 would be right there. And then 6, 30 would be right there. So what we see, it's not necessarily a perfect straight line, but what we see here, we could kind of generalize. We see a positive, right, appears to be a linear trend. And we're not really sure about how strong or how weak it is. Again, there's something that we could discuss called a correlation coefficient, which will give us a better idea of how strong or how weak this relation is, but again, unfortunately, this semester, just to kind of get through everything, we're going to skip talking about that, but we should at least feel comfortable with the basics of a scatter diagram or scatter plot, and plotting these points and kind of thinking about, do we have a positive trend or do we have a negative trend? Right. So we do want to talk a little bit about linear correlation. Okay. So correlation is used to determine whether or not there is a relationship between two quantities, and if so, how strong the relationship. The relationship must be linear if we're thinking about correlation. Both variables must be numerical. And the one big thing to kind of point out, again, we're not talking a lot about our strength here. We're skipping a lot of this section, but we do want to point out that correlation is not causation. And so in this next example, according to data obtained from the Statistical Abstract of the United States, the correlation between the percentage of the female population with a bachelor's degree and the parentage of births to unmarried mothers since 1990 is 0.940. Does that mean that a higher percentage of females with bachelor degrees causes a higher percentage of births to unmarried mothers? Right? So again, we're kind of skipping the part about this numerical value, what this 0.940 means. What that means is that there is a very strong correlation between these two. But what we want to think about and kind of focus on, is there an idea that both of these are increasing? Sure, there could possibly be data to support that both of these are increasing, but that does not necessarily mean that one of these causes another. Right? So does this cause something else to happen? Right? Anytime we see that, we're going to say no, that correlation is not causation. So certain things could be increasing or decreasing at about the same rate, but just because things are increasing or decreasing at the same rate doesn't necessarily mean that one thing causes the other to happen. Right? So just because there's a mathematical correspondence doesn't mean that one thing causes another thing to happen. All right, the last thing that we're going to talk about in this section is linear regression. Right, so what we're going to focus on for these last couple of examples is scatter plots where our data tend to form nice lines. Right, so there is a linear shape to them, being a straight line. So linear regression is a process of determining the linear relationship between two variables. Our goal is to describe this relationship using a linear equation. Again, there's a whole bunch of other statistical mathematics that we can use to actually create these ideas of these linear equations between these two values. We're not going to focus too much on that this semester, but we do want to talk a little bit about what that means. So what does this idea of linear regression mean to us? So the line of best fit, also called the regression line or the least squares line, is a line such that the sum of the squares of the vertical distance from the line to the data points is a minimum. Our regression line is our line of least squares or a line of best fit. So looking at our data, it is the best representative line or linear equation for our data. As we're thinking about these, our linear regression line we can use to make predictions. So that's one thing that we're going to do. It also provides us with a useful way of summarizing our linear relationship. And as we're going through these, remember that our x-coordinate is our independent variable and our y-coordinate is our dependent variable. So in these last couple of examples here that we're going to look at, right, we're going to look at interpreting our regression line. So as we're interpreting our slope tells us how much our y variable changes when our x value is increased by 1 unit. A slope close to 0 means there is no linear relationship. Our y-intercept is a predicted value when x equals 0. Our y-intercept is meaningful if it only makes sense for x to equal 0. Alright, so in example 2, there is a linear association between the height and weight of a sample of 6 women. Our regression line is given by weight equals negative 442.882 plus 9.029 times height. Now if we compare this to our idea of y equals mx plus b, right, what we usually think about for equations. Right? What we see here, we see these different values slightly rearranged. So we're going to see y equals b plus mx. So our y variable is our weight. Our y-intercept is our negative 442.882. Our slope is our 9.029. And our height is our x variable. Right, so if we are asked to interpret this, we're going to start with our slope. Interpret the slope and the y-intercept. So our slope is this 9.029. So we're going to say the slope tells us that the weight, which is y, increases because our slope is positive, 9.029 pounds for every 1 inch in height. Okay. So our slope tells us how much our y value either increases or decreases for every x value. Okay. The y-intercept tells us a woman 0 inches tall tends to weigh negative 442.882 pounds. Okay. In this case, it doesn't make sense to have a woman that is 0 inches tall. We can't have a negative weight. So we're going to say it does not make sense in this scenario. So again, our slope has to do with the change in y for every x. Our y-intercept tells us what happens if x equals 0. In some cases, it makes sense to analyze this. In some cases, it might not necessarily make sense to analyze our y-intercept. This is one of those cases of the latter. All right, let's look at one last example then. The scatter plot shows the association between the number of home runs and RBIs for the best home run hitters in the major leagues in the 2008 season. Can we predict the number of RBIs for a player with 25 home runs? If we look above this graph, we do have an equation. The predicted RBIs, that's our y, equals 30.46, and that's our y-intercept, plus 2.16, that's our slope, times our home runs, which is our x. Okay. So can we predict the number of RBIs for a player with 25 home runs? Okay. We're going to say yes. Okay. And what we're going to use is we're going to use this equation up here. So our predicted RBIs equals 30.46 plus 2.16 times our number of home runs, which is 25. And that is going to give us 84.416. So our prediction, a player with 25 home runs should hit about 84 RBIs. So we can use regression line equations to make predictions. Right, we're going to take whatever x value we're given, plug it into our equation, and get the predicted y value. Right, that's why we call them the independent and dependent, or predictor and response variable. Right, now we're also told to interpret the slope and the y-intercept. Right. So the slope tells us that for every additional x, which is an additional home run, so for every additional home run a player hits, they also tend to hit an additional 2.16 RBIs. So remember, our slope is our value that's connected to our x. It's that 2.16 that is connected to our home runs. The y-intercept tells us that a player with no, right, which is our 0, Y-intercept means our right value is 0. So with no home runs, tends to hit 30.46 RBIs. Right, so if X is 0, we have 0 home runs, what happens with our RBIs? Right? A player with 0 home runs tends to have about 30 RBIs. Again, the idea of linear modeling, linear regression, all of the stuff that we are looking at in this section, the basic shape, correlation, all of that stuff, we are just barely scratching the surface this semester. Again, normally if we were doing this face-to-face, we'd be talking a lot more about these different things in detail, but this should be kind of enough to tie you back to your basic algebra roots with your what is your slope, what is your y-intercept, and how can we use this to help us in statistical analysis.